Hello, I'm Hugh Mannfield and welcome to my science channel. Now today I'm going to be taking a deeper dive into Veritasium's video, the one that was about potential fields and how they manifest real effects when they don't represent anything actually physical. And this is all based on Lagrange's method of field potential. So in the video, Caspar goes into his descriptions of how Lagrange arrived at his method of field potential. And then he asked, so do these field potentials actually represent anything physical? And he concludes that most physicists say that they can't possibly have any physical significance. Well, when I think of it in terms of fluid space theory, the physical significance of Lagrange's potential is obvious, and let me explain what it is. So in 1777, Lagrange introduced the concept of gravitational potential, and it was a new method to help solve gravity problems. And it worked very well, although people weren't sure why it worked well because they didn't think that his field potential had any physical meaning. Well, let me start explaining by going back to Minkowski and his multi-space theory, his multi-space vision. Minkowski says, hereafter we would then have in the world no more the space, but an infinite number of spaces analogous as there are an infinite number of planes in three-dimensional space. So what he's saying there is when you go from two-dimensional space to three-dimensional space, suddenly rather than one two-dimensional plane, that is the only plane or surface, you suddenly have an infinite number of possible planes and surfaces. Now you take that analogy on to going from 3 dimensions to a 4-dimensional space, suddenly you don't have one volume of space, you have an infinite number of different spatial volumes that are all part of the same universe. Now that sounds kind of strange, but I can show you what he's talking about in terms of the space-time phase diagram. Here's our old friend. We have a distance axis on one axis, and we have time. It's a space-time diagram. And the bottom level represents the layer that would be considered to be at rest. You take your observer, he establishes, okay, I'm at rest, and then everything else is going to be moving relative to me. And as you build up those relative reference frames that have relative velocity along the spatial direction, you begin to get this shape, because as you increase velocity, the axes swing inward until once you reach the speed of light, they're along a straight line. So you end up with a space like this. And what this represents is all the possible reference frames on that one direction of motion that there can possibly be. And Minkowski's belief was that these are all equal, concurrent parts of space-time. All these different space-times exist together. So if an observer is on the base reference frame at rest, and there's another observer in some state of motion, he would appear on another layer. Now some of the other layers might be empty, but according to Minkowski, they're still just as valid, even though Einstein might say, no, talking about an empty reference frame in motion would be nonsense. Well, Minkowski's vision saw that these empty reference frames might still have relevance. Here's how it works. Let's say we have an observer at rest, and we have another observer in motion, and they both witness the same event. Now, to most people, this just seems like a natural thing. But why would an observer in a different space-time, because he's in motion, he has a different set of clocks and rods, so this observer exists in a different space-time from this observer. But they can still see the same events. They share a common cosmos. And this is the result of Minkowski's multispace. We all share the common cosmos no matter which reference frame we occupy. So now, in terms of fluid space theory, we look at a gravitational field. We can imagine an infinite series of inertial reference frames all falling inward. Now, they all fall inward at escape velocity. It's as if they've been released from an infinite distance and have had an infinite time to fall inward. So if a satellite or an object is moving around a circular orbit around the gravity well, it will be passing through an infinite series of inertial reference frames that have their velocity axis directed toward the center of the field. So every time it moves a little bit, it's passing from one inertial reference frame to another. Now all these inertial reference frames at the same radius have the same inward velocity, and that is escape velocity. And as you get closer and closer to the gravitational field, the velocity increases, and these reference frames become length contracted and time dilated along the radial direction, till eventually they form a gravity well. So what we have in a gravitational field, according to fluid space theory, and consistent with Minkowski's multispace, is a set of inertial reference frames that are all activated by the central mass. For example, some of these may be empty, and yet we can be pretty sure if we place an object within one of these reference frames, it will begin to fall into the gravitational field according to the acceleration field that exists within the gravity well. So all of these reference frames are potentially occupiable. They may not be occupied, but they have the potential to be occupied. And that's key in understanding the next point. If we look at a gravitational field like maybe the sun and the earth, the earth exists here, but there could be planets anywhere, potentially anywhere else in the field, and they would behave just as the earth is behaving within its part of the field. So if space is flowing in at escape velocity, but the reference frame is empty, there's no potential energy. But if we place a mass m into the field, co-moving with the flow field, it will have energy equal to 1/2 mv squared. And then if we plug in escape velocity, we get that the potential energy is gmm over r. Well, but if it doesn't have any mass, then it's just an empty reference frame. It's just a potential reference frame. So we can strike the mass term, and now we have Lagrange's potential. So really, Lagrange was possibly tapping into the unknown or unheard of velocity field within a gravitational field. So mainstream physics doesn't recognize the existence of an inward flow field within gravity or a velocity vector field within gravity. And yet, this is possibly what Lagrange's method of potential was tapping into. Now, there's a lot more that can be done with it. The velocity vector fields would be additive, and you could do a lot of different things with them if you admit that they exist. Imagine you have an entire new matrix or tensor that you can work with within general relativity, one that you can derive additional equations for. Well, this might actually help with solutions to the n-body problem or other things that we haven't been able to consider because we refuse to consider the existence of a velocity field within gravity. To wrap things up, I think There's a lot of potential left in the concept of fluid space theory, and if someone starts working with it, they should be able to derive new equations and discover new relationships within gravitational fields. And that's something to think about. So until next time, I'm Hugh Mannfield.